Swayam Prabha. Digital India. Educated India.
The reason we cannot have like an infinite computer that can, perform calculations all the way up to infinity is because, well, the very like bits can only get so small. And
what has that got to do with the Higgs mechanism or electrons or protons?
because
Which is what Professor spoke about.
because you can't divide like a quark further.
Can you divide a proton?
No, quarks can't exist on their own either, so I guess you can't divide a proton.
So where does that take us? Have you heard about some of the particle? Yeah, you wanted to say something.
Ma'am, Professor Prabha taught us the algebra behind quantum states, and here we learned that the Higgs particle is the quantization of the Higgs field. So in that way, is the mathematics related?
Why only the Higgs particle? What about a proton, an electron, a neutron?
Yes,
what about all of them?
Yeah, in that case as well.
So there is some mathematical structure underlying what Professor Bera said. And this mathematical structure that Prabha pointed out does not just have to do with what Professor Prafulla Bera said, or qubits and computers, quantum computing and information. It is the kind of mathematics that is also used in optics, for instance. It is used in various parts of quantum mechanics. It's used in particle physics. It is used in condensed matter physics. It is used in spin systems. So you see, the mathematics is kind of ubiquitous. The applications are in very many different areas. Ultimately, it is a question of identifying an appropriate linear vector space and describing objects with respect to that linear vector space. So I think Prabha has taught you about linear vector spaces. She has told you the properties of a linear vector space. She has even given you matrix representations. She has introduced the concept of basis vectors. She has. So suppose you have two basis vectors and you want to give column, suppose you have a two-dimensional linear vector space and therefore two basis vectors. They are orthogonal to each other. They are normalized to 1. So how will you represent it as a column? Give me the entries. 1, 0 and 0, 1. All right. So this is a two-dimensional linear vector space, and these are the basis vectors. How do you check that they are orthogonal to each other? The row and the column should give you a number, and that number is 0 if it is orthogonal. And 1, 0 with itself will give you 1. And so on, right? So these are basis vectors. Now you think of an atom. I'm giving you an example. I'm giving you an application. You think of an atom, and you know that in quantum mechanics, energy levels are quantized. Energy levels are discrete. So you think of an atom which has got energy levels like that. They are not equally spaced. Many atoms do not have energy levels which are equally spaced. And suppose I do an experiment where I shine light which has energy equal to this energy gap, then transitions are most probably going to happen only between these two levels. So the drama is described by a two-level atom. Essentially, I can neglect the other levels and I can think of it as a two-level atom, because transitions going from here, there, or there, here, the electronic transitions, there is a very large probability that it happens only between these two levels. In that case, I can model this whole thing as a two-level atom. There are very many experiments that are done with 2-level atoms. You choose 2 levels, largely in the alkaline atoms, and choose 2 levels and do all kinds of experiments, including your quantum computing experiments. Now, just to give a notation and to familiarize you with the Dirac notation that she has taught you, as far as these 2 levels are concerned, this is the ground state. I need to put a symbol inside the ket, and she has taught you about the ket. And this is the excited state, so I'm going to put an E out there. The whole business of atoms interacting with light is atomic physics. So light is shone and things happen inside this atom. The mathematics is the mathematics of a 2-dimensional linear vector space. Now this state is obviously different from this state. How do you decide that 2 states are different? At least one property that you measure should be different. I mean, how do you know the 2 people are different? At least their nose should look different, or their eyes should look different, or their height should be different. At least one property should be different. Here the energy is different. This is the excited state. That is the ground state. Therefore, these 2 are orthogonal to each other. Therefore, I write this. As you know, all these things can be represented by columns and the corresponding rows. So I could represent this by this column and this by this column. These are the basis states in this 2-dimensional linear vector space. So here is your first application in atomic physics. This is true. I have chosen it so that this is true. Because this is 1, 0 and this is 0, 1. Now it's an easy thing for you to check out that all this is true. This clear?
Orthogonal to each other.
I'm not assuming it.
Why are they orthogonal?
Because they have at least one property which is different from each other. You are not him because you have at least one property which is different from him. There is a certain uniqueness between the 2 of them. Now you can ask me, maybe we can have a hybrid of 2 things. You could, and that is the superposition that she was talking about. For instance, if I have an object like this is some constant. This is obviously not orthogonal to E or to G. There is a component of E in it, there is a component of G in it. So when you superpose basis states, the superposition is not going to be orthogonal to either basis state. If you have in a plane unit vector I and unit vector j, they are along different directions. That is what separates them. Therefore, I and j are orthogonal to each other. But if I had 5i plus 4j, it is neither orthogonal to I nor orthogonal to j. It has a component along both.
Since the ground state and the excited state is like independent, is that why we are saying that they are orthogonal?
There is at least one property which is different.
Okay, but how does that translate to it being orthogonal to each other?
Because I cannot describe this fully using that. Okay. In fact, I will miss out on this. I cannot use movement along the x-axis to describe movement along the y-axis. Yes. I cannot define a point on the y-axis by just looking at points on the x-axis. Wonderful, all the better. They're still orthogonal. That is still orthogonal. But when do you define a state? Now I'm going to digress a bit. Professor Behra was telling you that there is a proton and an antiproton. So what's the difference between a proton and an antiproton? Only charge. The proton and electron have opposite charges. So is the electron an antiproton? The mass is different. Okay, So the electron, the proton and the antiproton, do they have the same mass or do they have different masses? So the mass is the same, the charge is different. Is that all? So there is one property which is different. Now you said, are there more properties which are different? So are there more properties which are different between the proton and the antiproton? Spin is the same. They both spin half particles. Lots of things are different. Sorry? No. No. Between the proton and the antiproton? No. There are other quantum numbers. There is this thing called baryon number, and that is different. There is this thing called isospin, and that is different. So when Professor Behra says everything is opposite, well, you should understand what is the negative of the proton's property, what is not, and why is it so. So this is an example where more than one quantity is different between the proton and the antiproton. It is not just the charge which is different. The mass is the same, the rest mass is the same. The spin is the same. However, the baryon number is different, for instance, and so on. Isospin is different. And so
Ma'am, if another vector is there at an angle theta with one vector.
you're in the plane.
Yes, ma'am. Then also the vector at angle theta cannot be fully described by this vector.
Yes. But there is a component along this. There is a projection along
So
this.
there are some things which are same, but there are things which are different.
That's
you,
right.
you just,
Here in this problem, I only have energy, and that is different.
That's why we are telling.
Yes, yes.
So does the superposition represent the probability of finding an electron at each state?
We are not talking electron in this problem. We are talking about an atom with two energy levels. This superposition, this is the probability amplitude. This is the probability of finding the electron in state E. And this is the probability of finding the electron in state ket G. The total probability, the electron has to be somewhere, and these are the only two states allowed. Well, not the electron, in this case the atom. So the total probability should be 1. Yeah.
You mentioned these are the quantum numbers for the proton. For example, in school, what we learned was that the 5 major quantum numbers came from Schrodinger's equation. Do these quantum numbers also come from Schrodinger's equation, or do they come from
Which are the quantum numbers that come from Schrodinger's equation? I would like to know. Sorry?
principal quantum number?
No. That's okay, fine. N, L, M, and so on. I think you're talking about the hydrogen atom or something like that. All right, an atom in general. For that system, you write the Schrodinger equation, you solve the Schrodinger equation, and you will find that there are these quantum numbers, which are conserved. They are the good ones, they are conserved. For a given, that means that to define the basis state, you need to put in all these labels, N, L, and M. The Schrodinger equation, you start with the Schrodinger equation, you solve the Schrodinger equation, and you find out what are the labels inside the ket. That's a procedure. The system exists independent of the Schrodinger equation. Yeah.
In school, we were taught these are the four major quantum numbers. So, ma'am.
No. That is for a certain set of problems. Yes. Atoms.
Ma'am, so what is quantum number defined as?
Okay. So how do I describe you? Let's go the Behra way. Let us try to popularize this. So how do I describe you?
By
your height?
Yes, ma'am.
Does it change if you move from place to place?
No.
Your weight, as long as you don't go eating too much? No. If you just move from place to place, does it change? No. The shape of your nose? Shape of your eyes? A set of quantum numbers define a quantum system. Like you are defined by your height, your weight, the shape of your nose and so on. But understand the following thing. These are descriptors of you. They're not going to change because you're moving around. Your nose doesn't change because you're moving around. So an electron has spin minus E, minus 1 times E, wherever it is. It has got spin half, wherever it is. It has got lepton number 1, wherever it is. So a set of quantum numbers are the descriptors of a system, a particle or an atom or anything. In this problem, there is only one quantum number we are dealing with.
How many total quantum numbers are possible for a given atom or a electron or something?
Okay, now that depends upon the system that you're talking about. This definitely involves some mathematics. I'll have to introduce something called commutation. I will introduce commutation. Maybe Prabha has already talked about commutators. I don't know. And then I will tell you how many quantum numbers there will be. Just a little bit of waiting and we will get there. Is there anything else?
Why do we need to represent the two states as a two-dimensional vector space?
I'm saying that in a plane, for instance, if you have to describe an arbitrary vector, don't you need a unit vector I and a unit vector j? In general, the state of the system would be this, where A is something and B is something else. I need these two objects in terms of which I define it.
Okay, so they're not any specific.
Well, not necessary. I could have chosen this. But I need two, because it's in 2 dimensions. This is a rotation by 45, if you understand what I mean, right? I plus j by root 2 and I minus j by root 2, they are perpendicular to each other. That's what I'm doing. So it doesn't matter which two, but there are only two. And I need those two to describe any state.
I don't understand why we define it like.
Just take a plane. I don't have unit vectors I and j. So what do you want to do? How do you describe an arbitrary vector? Suggest.
Yeah, we need the coordinate plane, I get that. But
Then
I don't get like why ground state and.
forget all this. Take the plane. Unit vectors I and j. So you don't want them. So what do you want?
No, I'm not saying I don't want them. I don't understand it.
Do you understand that?
Yes.
Then why don't you understand this?
Because like.
Simply because I put it inside a ket?
Yeah.
No, there are 2 dimensions. These are the analogues of 2 perpendicular dimensions because they have properties which are different from each other, like unit vector I and unit vector j. These are just the analogues. But instead of choosing I and j, I could have chosen I plus j by root 2 and I minus j by root 2, which are perpendicular to each other. I could have chosen this. But I only need 2 vectors. Every vector in the plane can be written in terms of 2 orthogonal, normalized to 1 basis vectors. Now, which 2 you choose is your business. You can choose what you want. You may choose I and j. You may choose I plus j by root 2 and I minus j by root 2. You may choose any pair which is orthogonal to each other, but stick to that plane.
No, but why ground state and excited state?
These are the experiment that I am talking about has only these 2 levels which are of interest. If the experiment involved more energy levels, then I would have needed all of them. I am talking about an experiment where any transitions are only between 2 levels. So I can forget all the other levels. And therefore, what is of relevance to me is a 2-dimensional linear vector space in which I do my mathematics. And those are the 2 levels in which the physics is happening. That's why. I would not do this if there are 3 levels which are involved in the experiment. Obviously, if I have x, y, and z, I cannot describe every vector by I and j. I will need I, j, and k. Right. So, yeah. Anybody says something? Can I move on? All right. So here we go. I want to show you something interesting. You've been given these columns and you know the corresponding rows. And you know how to take an inner product and show whether it is 0 or 1 or some number. But do you know how to construct a matrix given these columns and rows? You're given this. You're given this and you're given this. So you have 1, 0, 0, 1, you have 1, 0, 0, 1. How do you construct a matrix out of this? If you did this, you got a number. So you put the ket on that side, the bra on that side and the ket on this side, you get a number. What should I do to get a matrix? After all, if you have columns, something should act on it. Otherwise, we can all go home. Only a 2 by 2 matrix can act on a column, a 2-componented column. How do you get a 2 by 2 matrix out of this? No vectors. I want a matrix. What? Let me just help you. What if you did this? This guy is a column. This guy is a row. What will you get? Tell me, what are the entries? Sorry? You get a matrix. So you do this and you will get a matrix. You do that and you will get a number. Don't say adding. You're not adding. There is no plus sign. So he's saying this. Sure, I agree. But it involves putting the ket on that side and then the bra. Now your ket could well be a combination, a superposition. That's all different. I'm saying it's a ket and a bra. Agreed? Yeah.
Ma'am, we can also take the ket of E and the bra of G and we'll still get a 2 by 2, right?
Of course. What else?
E and G, like.
Sure. What else? And for any arbitrary state psi, a psi and a psi. Sure. You can do this. You can do this. G also. But now you know. That's how you get a matrix. Why do you need the matrix? Well, what do you do with the column? Unless you have a matrix which acts on the column to give you another column. What would that mean physically? You see the column, let us say I'm looking at this column. So I'm looking at the state G. Some matrix acts on the state G. In the experiment, what can happen? In the experiment, what happens between G and E? I shine light on it. Then what happens? This might go there, or that might come here. This going from here there, or coming from there here, should be explained mathematically by an appropriate 2 by 2 matrix acting on that column to give you another column. So for instance, suppose I take this matrix. We are agreed that this is a matrix. I want to make it act on this ket G. But this is 1. So this gives me ket E. This is the mathematics which tells you that something acted on ket G, the something being photons. You shone light on the atom and it took it to ket E. The atomic transition from the ground state to the excited state is described by this operator in a two-level atom. Now I want something which will act on ket E. Give me the operator which will act on ket E. The matrix is an operator. It operates on a state. So give me an operator which will act on ket E and give me ket G. I want to lower the energy. Got it? There are only two levels. So what will happen when this acts on E? 0. There are only two levels. There is no third level to which it can go. This part clear? Yeah.
Can you just explain the transition, like in each of these cases that you've written, from where is the electron going? Like, is it ground state to excited or excited to ground? Just
the electron is in the ground state. This is the operation of shining light and taking the ground state to the excited state, which means the electron went to the excited state. This is the operation of shining light and taking the electron from the excited state to the ground state. No other case is possible in this simple model. But you shouldn't imagine that it is just a simple model. This is what many experiments are about. Because as I said, experimentally one realizes two-level atoms, three-level atoms, four-level atoms. So the drama is confined to those levels. And we work with those.
How do we find the operator of the photon we have shined on the electron?
I'm not even looking at the photon now. Okay. That's a separate problem. I'm looking at the atom. So we already know what the operator is. I may know, I may not know. But the experiment is designed to look at the atom and what happens to the atom. You can design experiments to look at what happens to the photon. That's a separate matter. You forgot what to ask. Well, you don't have to ask. When you remember, you ask. Just interrupt and ask. Is that okay? All right. Anybody else? All right. Now let us do something more beyond this.
Yes, ma'am. Sorry to interrupt.
Now you remembered what to ask.
Yes.
Yeah.
Ma'am, why can't the 2x2 matrix act on a superposition?
It can. It can.
It can act on any state.
I'm giving you how it acts. You see, you're asking me what happens when there is something that acts on 5i plus 4j. I'm still in the business of telling you what happens when it acts on I and what happens when it acts on j. It will. Definitely yes. All right. But look at the structure of these matrices, and I shouldn't have erased it. So let's just write that down once. What is EE plus GG? What matrix is that? Identity. This is called a projector onto ket G. This is called a projector onto ket E. And what I have given you is just the statement that the sum of the projectors onto all the basis states is going to be the identity operator. Look at this matrix. Can you say something about its properties? Suppose I take the complex conjugate of this matrix. They're all real entries. Will it change? No. Suppose I take the complex conjugate and the transpose. That means interchange the rows and the columns. Will it change? No or yes? No. It's a Hermitian matrix. It's called a Hermitian matrix. you know, eigenvalues of all Hermitian matrices. That means the matrix is the same as what you will get if you took the complex conjugate of each entry and took the transpose. Well, you could have taken the transpose and then taken the complex conjugate, doesn't matter. If that resultant matrix is the same as the original matrix, it's called a Hermitian matrix. The matrix and its transpose conjugates are the same. Dagger means take the transpose and take the complex conjugate. What is interesting about this is an example of a Hermitian matrix. What is interesting about Hermitian matrices is their eigenvalues are real. It can be established pretty easily that the eigenvalues of a Hermitian matrix are real. Yeah.
Mom, can you repeat what the Hermitian matrix?
Sorry?
Can you please repeat what the Hermitian matrix?
Take this matrix. I'm giving you an example of a Hermitian matrix. First, take the star. Take the complex conjugate. Does it change? No. Each entry, no, wait, I'm just answering. Each entry, just take the complex conjugate, but this is real, it doesn't change. If the entries were complex numbers, it would have changed. Doesn't matter, here it doesn't change. Take the transpose. There are two operations you should do. One is take the complex conjugate, the other is take the transpose, which means interchange the rows and the columns. If you interchange the rows and the columns, this 1, 0 will go there, this 0, 0 will go here. Nothing changes. A Hermitian matrix is one. That operation, the transpose conjugate operation, is represented by the symbol, the dagger, not plus, dagger. If a matrix H is equal to its dagger, then it's a Hermitian matrix. I mean, for all practical purposes, that definition will do. I'm not being extremely precise, but this should do. Yeah. Okay, suppose I have a matrix 1 plus I, 2 minus 2I, 3 and 4I. Take the complex conjugate of each of them. 1 minus I, 2 plus 2I, 3 and minus 4I. That's the complex conjugate. Then interchange the rows and the columns. But in this matrix, that complex conjugate operation doesn't make any meaning. Yeah.
Ma'am, what is an eigenvalue?
I'll come to that. We'll get to all that. That's a long story.
Could you once again?
If I take this projector onto E and make it act on that psi, this is a number, I can pull it out. So this term doesn't contribute. So it projects the component of psi onto E. You do the same thing with G. You will get BG. The sum of projectors will be identity. Identity operator. How much time do I have? Yeah, maybe in 5 minutes I'll wind up. This is an example that I gave of a two-level atom. Professor Behra spoke about protons, neutrons, electrons. There too it is the same mathematics. There is a quantum number called spin. Have you heard of spin? Who told you about spin? In school? So what is the spin business? What is it? So what is spin? What do you mean when you say the spin of the electron is half? Let me ask you, let's go through this properly. When you say the spin of the electron is half, do you mean it is spinning like this? Do you mean it is spinning like that? It's just a quantum number. That value is half. That's all that it means. How many projections of spin are there along the z-axis if the spin is half? The upstate and the downstate. What are those values? So, take an electron. It is a spin half particle. That's very funny because does spin have dimensions? Yes. When you say that the electron has spin half, what do you mean? There is some object which you are not talking about. You are saying half in units of something. Sorry? In quantum mechanics, what is this basic object? Okay, let me give you a clue. Spin has the same dimensions as orbital angular momentum. Has the same physical dimensions as orbital angular momentum. Do you know of a fundamental constant in quantum mechanics which has the same dimensions as orbital angular momentum? The Planck's constant. So when you say that the electron has spin half, you mean it is half in units of h bar, which is h by 2 pi. The 2 pi doesn't add to the dimension. The h certainly does. So what is the dimension? Energy second. Joule second, if you wish. So when you say that the electron has spin half, you mean it is half h cross. That is the spin of the electron. Spin cannot be negative. But if spin is a vector in 3 dimensions, it has 3 components, one along x, one along y, and one along z. Choose any one of these as your reference axes. International notation is to call it the z-axis. Then, if the projection of spin along z is plus half, its sz value is plus half h cross, or it is in the upstate. If the projection of spin along the z-axis is minus half, then the electron is in the spin down state. That's what you mean by spin half. How do you distinguish an electron in the spin up state from an electron in the spin down state? What is the object, what is the property that is different? What is the quantum number which is different? Here I said energy is different. So an electron in the spin up state and an electron in the spin down state, what is it that is different? Spin is half. The third component of spin is z. It's either plus half or minus half. So to distinguish an electron in the spin up state from an electron in the spin down state, it is the third component of spin, or the projection of spin along the z-axis, that tells you the difference. When you say spin up, you mean the projection along the z-axis is half h cross. When you say it is spin down, it means a projection of spin along the z-axis is minus half h cross. Then, how many basis states are there if I have to talk about the spin of the electron? What is the linear vector space dimension, the relevant linear vector space? The dimensions of the relevant linear vector space. 2D. How many basis states are there? The electron with spin up and the electron with spin down. So plus half and minus half. The ket with plus half in it and the ket with minus half in it. That's another example of a 2-dimensional linear vector space. So Prafulla Bera mentioned the electron. The proton is another spin half. Another 2-dimensional linear vector space in spin. Neutron is another spin half. Another 2-dimensional linear vector space in spin. Yeah.
Ma'am, you said that we only consider this as z-axis projection of the spin. Why don't we take the x and y?
You might want to call z as x.
No, ma'am. If we consider
now that
why
brings
not?
us to a very important and interesting problem in quantum physics. Can you simultaneously measure the component along x, y, and z to arbitrary precision? You cannot. That's why. There is an uncertainty in simultaneous measurement. You can only measure the total spin, which is half, whether it is in the upstate or in the downstate, and any one component of spin simultaneously to arbitrary precision. We call that z.
Ma'am, so let us say that 2 scientists are there and they're trying to measure an electron and they agree which is z, which is x, which is y. So one scientist decides to go with the z-axis. Why can't we go with that particular x-axis which is not the same?
If you measured the spin along z completely to arbitrary precision, along x and y you will get expectation values or average values. You can find the average value of Sx and the average value of Sy. Yes, you can do that. and you will find the exact value of Sz. That's what you will do. Yeah.
Ma'am, what is a H cross?
What is the?
H cross. You told projection along z-axis.
No, H is Planck's constant, and I will let you as a homework find out the numerical value of the Planck's constant. Excellent. That is H cross. H by 2 pi. Okay. That one has dimensions because of the H, not because of the 2 pi. Physical dimensions is that of energy time, joule second. And that's the same dimension as angular momentum. So spin has the same physical dimension as orbital angular momentum. But orbital angular momentum is r cross p. So if you change p, for instance, L can change. You can't change the spin of the electron. It's like changing your nose. You can't do that. An electron here and an electron there and an electron there will have spin half. It's one of the quantum numbers that defines the electron.
Ma'am, when we consider a linear vector spaces its spin, do we, does it mean that the spin up and spin down is normalized to half?
Normalized to 1 each.
One each. And, what is this?
Like ket E is 1 and ket G is 1. Yeah. The inner product. The inner product is 1. Is there anything else? Yeah. You want me to sum up? I've just begun.
No, actually, some of what you told now, because I haven't read this, so that can't really be. Spin is joules per second. And
No, that's the physical. Joules second, not joules per second.
joule second.
Spin has the same physical dimension as angular momentum. And it has the same dimension as the Planck's constant, which is energy second. Yeah.
Yeah, and the total spin, like plus or minus half, we get it by finding the projection of spin in each axis.
Not total spin. Total spin will always be plus half.
Yeah, so
The projection will either be plus half or minus half.
the projection is plus or minus.
That's right.
The total spin is
Half.
always.
An electron is defined by spin half.
And so what is this? So what does it tell us? What is the objective thing that it tells us?
It tells you that the electron can exist in two states. Both states have spin half, but it could exist in the up state or in the down state. The up state defined by the projection plus half along Sz, and the down state defined by minus half along Z. Those are the numbers. If you made a measurement, if it is in the up state, the component of spin along Z will be plus half, otherwise it will be minus half.
What does being upstate?
Being upstate means having component of spin equals plus half. You make a measurement, you put it in a magnetic field. That's what the Stern-Gerlach experiment was all about. You find out how many of them align, if you put a strong magnetic field, sufficiently strong, how many of them align along the up direction, which you have defined. That's the direction of the magnetic field.
Okay, so when you put a magnetic field, some go up, some go down.
Yes. On an average, you can talk about how many go up, how many go down, and so on. But each electron would be in a plus half state that's aligned along the magnetic field, where the magnetic field defines your positive Z direction, or it aligns against the magnetic field. Yeah. So that's the connection with the experiment. The famous Stern-Gerlach experiment. Okay. They what? Of course, because there's one property that's different. So here I've given you two examples. One is a two-level atom where there are two energy states which are different, and they are the basis states in the two-dimensional linear vector space. I've given you a completely different problem, which is an electron, because it can exist in two states of Sz, and that's another two-dimensional linear vector space. That has nothing to do with this. I'm giving you examples. The maths is the same. The physical situation is different. One is a two-level atom. The other is a single particle, an electron with spin half. But the math is the same. It's a two-dimensional linear vector space. I think the moral of what I have said till now is that the underlying mathematics, there is a commonality between seemingly different problems in physics. You need the math. Without the math, you can't do quantum mechanics. I think Professor Balakrishnan must have told you that it is inevitable that you understand mathematics to do physics. You cannot do it otherwise. Your common sense will not take you anywhere. In fact, you will be coming up with very bizarre results, neither experimentally provable or mathematically viable. That is what you will come up with if you relied on your common sense. The point that I am trying to make is, if you look at the two-dimensional linear vector space, the number of basis states, and so on, that math can be applied to very many distinctly different physical situations. I gave you two examples. One is the two-level atom, where the basis states are the energy states, Kt and Kg, nothing to do with spin. I gave you a very different example, the electron. Spin up and spin down are the basis states. There are many more such examples. So I think that is the take-home message for today's lecture. I think I'll stop here. Yeah.
Ma'am, about 8 different professors have come to us and talked about spin. What exactly is spin?
What exactly is spin? I will answer that question. Yeah. I will answer that question if you tell me what exactly is charge. You tell me what is electric charge. You must have known all about it. They've taught you electromagnetism or electrostatics or whatever.
Ma'am, charge is like a measure which we use to we use to calculate how much effect, electrostatic effect, electromagnetic effect a particular particle will have.
What does that mean?
So, for example, we can measure.
You mean if you take a charged particle and put it in an external field, magnetic field, it will deflect in its track. Is that what you're saying?
Yeah, kind of.
Is that what you're saying? You're saying that if I put it in the field, the charged particle will interact with the field and therefore change its direction. Is that what you're saying? Well, that's the experiment. Well, here you put it in a magnetic field, and Stern and Gerlach told you that it will either point up or down.
And so it's basically magnetic charge.
It's not a magnetic charge. It's something that responds to a magnetic field. It's a property.
At some stage, I'll explain to them that it's the eigenvalue that has to be operated over the boundary.
Yeah. So you see. No, let me ask you, what do you mean by nose? N-O-S-E, nose.
Nose.
What's that? What's that? I think so, the failure of intuition. You know, to answer that question, you will say, see, finally you will come around to saying, see, my nose is this size and his nose is that size. So basically, it's a property, it's an attribute to describe things. Spin is an attribute. I mean, particle physicists are also, they have this very strange sense of humor. There are quantum numbers called beauty, truth, charm, you see, color, flavor. I mean, it's not a mirch masala thing. I mean, so these are attributes. There's nothing more to it. Sorry? Quark. Yeah. Yeah. Charm. The charmonium, it's a bound state of quarks, the charm quark and so on. Yeah. Nothing, it's a quantum number. Yeah.
So you asked him, like, what is the nose? I believe that nose is the entrance passes to the nasal.
What does that mean? You're using the word nasal.
To the esophagus.
What is esophagus? So you see, you're now going on adding more and more and more things, all that to distinguish between two people. Finally, it comes to that. It defines you.
No, we breathe through the nose. So
What do you mean breathe? What is that?
taking air.
What does that mean? You're not answering my question. It is an attribute of the human being or of a living being, or it's an attribute. Finally, it comes to it's an attribute. You can't explain it better. It's an attribute. That is how I distinguish between you and him. That's one of the properties. You're adding more and more words.
Ma'am,
You have to use something else to describe this.
number.
No. Two particles may have some properties which are shared. For instance, the proton, the antiproton and the electron have negative charge. But there are other properties which are different. So to distinguish them, one different property is enough.
Yes, ma'am. What does spin physically signify?
What
is
does-
the physical significance of spin?
I think. What do you mean by physical significance?
Or like physically represent.
You have to understand something at a fairly deep level. Okay, if I ask you, if I show you a piece of chalk and say, "What is this?" You'd say it's a piece of chalk. If I ask you, "What is chalk really?" What would you say? You would start telling me it's calcium sulfate molecules, and then I say, "What is that really?" So eventually, it gets down to realizing that the name that you give an object is only a shorthand for the collection of its properties. That's all it is. There is no such thing as what is really something. It's just a collection of its properties. Now it so happens, and let me say this, I was going to say it at some time or the other, it so happens that classical physics, normal classical physics, you can categorize objects into two categories, broadly speaking, like waves and particles, for instance. Particles would be rigid objects with momentum, energy, and so on. They'd be localized. Waves would have broad properties, like they would be able to transport energy. They would have a wavelength, a frequency. They're diffuse in nature. One is not the other, classically. But in nature, there exists, and beyond our range of human perception, there exist objects which have some properties from this basket and some from that basket. What would you call them? Would you then, therefore, there are questions like in the early days of quantum mechanics, is it a wave or a particle? And people said it could be called a wavicle. That doesn't do anything for me at all. The fact is there exist objects which go beyond normal physical intuition in the world of middle dimensions when you go to extremely small objects and extremely large objects like the universe. And you need a different language, which happens to be mathematics. Normal words lose their meaning. And depending, further thing that happens in the case of elementary particles is that depending on what property you probe, it shows the property either belonging to this basket or that or a mixture of the two. So these crazy things can happen, and it goes beyond what you would call normal intuition. Okay, so we'll talk more about this. It's just a failure of what might call physical intuition or common sense, but there's a way of getting around it. And spin is one of those properties. We will talk a little more about spin as time goes on.